Now I would like to make a number of remarks on the relation of mathematics and physics, which are a little more general. The first is that the mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now I explain that. If you state the axioms, you say such and such a so, and such and such a so, and such a so, what then? Then the logic can be carried out without knowing what the such and such words mean. That is, if the statements about the axioms are true, are carefully formulated and complete enough, it is not necessary for the man who's doing the reasoning to have any knowledge of the meaning of these words, and he'll be able to deduce in the same language new conclusions. If I use the word triangle in one of the axioms, there'd be some statement about triangles in the conclusion, whereas the man who's doing the reasoning might not know what the triangle is. But then I can read his thing back and say, oh, a triangle, well, that's just a three-sided what have you, that's a so-and-so. And so I know this new fact. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. It's necessary to, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true. And this is a problem which is not a problem of mathematics at all. I've already mentioned one other relationship that, of course, it's obvious how the mathematical reasonings which have been developed are of great power and use for physicists. On the other hand, sometimes the physicist's reasoning is useful for mathematicians. Mathematicians also like to make their reasoning as general as possible. If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space. You know, you're in it and you measure distances and there are three numbers you need to tell where something is. You go breadth, width, and height, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in a special case. He's never interested in the general case. He's talking about something. He's not talking abstractly about anything. He knows what he's talking about. He wants to discuss the gravity law. He doesn't want the arbitrary force case. He wants the gravity law. And so there's a certain amount of reducing, because the mathematicians have prepared these things for a wide range of problems, which is very useful. And later on, it always turns out that the poor physicist has to come back and says, excuse me, when you wanted to tell me about the 4 dimensions,